Hey everyone, welcome to this explainer of our source material. If you're a college student staring down a mountain of electrical engineering coursework right now, I just want you to take a deep breath. Seriously, we're going to set aside that high-pressure lecture hall vibe today and just have a calm, focused conversation. We're going to demystify the absolute foundations of electrical engineering together, and we'll transform what probably looks like a chaotic jumble of math into an elegant, totally understandable system.
Have you ever actually stopped to wonder what drives the electricity in our walls? I mean, we flip a switch and boom, light floods the room. We plug in a completely dead phone and it instantly comes back to life. But behind the drywall and inside those charging cables, there's this invisible, silent traffic that's literally powering your everyday life. So today, we're going to learn the hidden rules of that road.
Okay, here's our comforting roadmap for today. First up, the spark of electricity. Second, we'll meet the circuit elements. Third, we'll cover the laws of flow. And finally, number 4, solving the puzzle.
Let's jump right into section 1, the spark of electricity, understanding the fundamental particles.
Right, so before we can understand how a sprawling city's power grid works, or, even just the circuit board in your laptop, we have to start at the absolute microscopic level. And it all begins with this unimaginably small number, negative 1.6 times 10 to the power of negative 19 coulombs. This tiny value, which is detailed right in our source notes, represents the electric charge of a single solitary electron. It is microscopic. But when you get enough of these electrons moving together, there's enough power to light up entire cities. Grounding ourselves in this tiny number kind of helps us realize that all of electrical engineering is really just the art of managing these incredibly small charges.
Okay, let's dive into this flow. When those tiny charges start moving, we get what's called electric current. Current, represented by the letter I, is just the rate of flow of that electric charge over time, measured in amperes. Honestly, just think of it exactly like the flow of traffic on a highway. The charge is the cars, and the current is simply how many of those cars are driving past a certain point every single second. That's it. It's just a measurement of flow.
But here's the thing. Cars don't just move on their own, right? Something has to actually compel them forward, and that brings us to electrical potential, which you probably know better as voltage. Our notes define voltage as the amount of work done to move a unit positive charge from one place to another. So, going back to our highway analogy, if current is the traffic flowing, voltage is the underlying pressure. It's the motivation forcing those cars to move. Without voltage, that traffic just sits perfectly still.
Now, when you combine that moving traffic with that driving pressure, things actually get accomplished. This is electrical power, which equals voltage multiplied by current, or P equals V times I. Power, measured in watts or joules per second, is simply the combination of that flow and pressure doing actual tangible work. We're talking about spinning a motor or illuminating a light bulb. It's the satisfying real-world result of all that microscopic movement.
All right, moving on to section 2. Meet the circuit elements, the roads and toll booths of our electrical city.
So now that we understand the invisible flow, we're going to shift our focus to the physical roads, toll booths, and intersections that actually manage it. In our electrical city, we can divide our components into 2 main categories, active and passive elements. Active elements, well, they're the engines of our circuit. These are your voltage and current sources, think batteries or generators, that supply energy into the system. On the flip side, we have passive elements. These are the roads and obstacles, like resistors, inductors, and capacitors, that receive, dissipate, or store that energy. You absolutely need both to have a functioning system.
We can also categorize these elements by how predictably they behave. Linear elements follow Ohm's law perfectly. They have a nice, predictable, straight-line, proportional relationship between voltage and current. You push twice as hard, you get exactly twice the flow. Nonlinear elements, on the other hand, do not strictly follow Ohm's law. Components like diodes have a much more complex conditional behavior. They act a bit more like a one-way street or maybe a strict security gate in our city.
And this brilliantly illustrates exactly what these passive components look like on paper. Looking at our source notes here, we see the actual symbols engineers use to map out these elements. You've got the jagged line of the resistor, the coil loops of the inductor, and the parallel plates of the capacitor. When you see these symbols, honestly, you shouldn't feel intimidated at all. You're just looking at a simple, top-down map of energy speed bumps and storage tanks.
Let's look at section 3, the laws of flow, the universal rules of electrical traffic.
When you connect all these components together, they have to obey absolute non-negotiable laws of physics. Notice how the currents here, represented by I in this diagram, intersect at a central point, which we call a node. This visually anchors our first major rule, Kirchhoff's current law, or KCL. It might look a little messy at first glance, but the concept it represents is incredibly simple and intuitive.
So, the absolutely crucial point here is that Kirchhoff's current law simply states that the sum of currents entering a node exactly equals the sum of currents leaving that node. In other words, the algebraic sum is zero. Just think about it calmly for a second. KCL just means no cars can magically disappear at a highway intersection. Whatever traffic flows into the junction absolutely must flow out. It's really just a junction rule for our electrical traffic, keeping the universe in perfect balance.
Building on that, notice the looped circuit drawing right here in the notes. This closed rectangle represents our second fundamental rule, Kirchhoff's voltage law, or KVL. Notice how it traces a complete path from the voltage source, through the resistors, and right back to where it started. KVL states that the algebraic sum of voltage drops around any closed path or loop must be zero. If you think of voltage kind of like elevation, KVL is just a round-trip hike. If you start at base camp, hike up a mountain, hike down into a valley, and then return to the exact same base camp, your total change in elevation perfectly balances out to zero. You always end up exactly where you started. Finally, Section 4, Solving the Puzzle. Analyzing complex networks step by step.
Now we're going to see how engineers apply these simple rules to solve seemingly intimidating networks without ever getting overwhelmed. I know, this wall of dense math looks terrifying. It's the exact kind of thing that causes a cold sweat in a lecture hall. But take a breath. It's actually just demonstrating a beautifully simple, repeated process called the superposition theorem. It's not one giant impossible calculation. It's really just a small, easy calculation done a few times over.
Here is how you conquer that math calmly, step by step, using superposition. Step 1. Isolate just one energy source acting alone and pretend the others don't even exist. Step 2. Calculate that single source's individual effect on the circuit. Step 3. Repeat that for the other sources, and then simply add up those individual effects to find the true total effect. You're just dividing a really complex problem into single, completely manageable pieces. Divide and conquer.
And here is your peaceful, practical takeaway for today. All the incredibly complex electronics in our modern world, the smartphones, the servers, the life-saving medical equipment, they all simply boil down to these few foundational rules of traffic and flow. You do not need to be a math genius to appreciate this. You just need to realize that circuits are elegantly organized systems, obeying incredibly reliable laws of nature. To validate everything we've covered today, let's look at this direct quote from our textbook notes. A circuit is used to model the behavior of physical, electrical, or electronic systems. These laws obey the principle of superposition and homogeneity and are hence linear. I know it sounds super academic, but it's really just a promise. Electricity is predictable. If you learn these basic laws, the system will always tell you exactly what it's going to do.
So, we've walked the path from microscopic electrons to full circuit analysis, all without breaking a sweat. Now that you know the hidden rules of this electrical road, how will you look at the devices powering your life differently? The next time you plug something in, I hope you take a second to appreciate the quiet, organized traffic flowing just beneath the surface. Thanks for joining me for this explainer, and keep learning.